Number 4, and so I'm just going to record this, and I'll post this out there. And if we have some time, we'll go ahead and go through number 5 as well. So number 4, go ahead, clean this up on a separate page. Copy this. Okay, so number 4, it's a no calculator problem, and it says let h be a function defined for all x not equal to 0, such that h at 4 equals -3, and the derivative of h is given by h prime at x is equal to x squared minus 2 over x for all x not equal to 0. Okay. Okay, and then we're asked to do 4 things. Find all values of x for which the graph of h has a horizontal tangent and determine whether h has a local max, local min, or neither at each of these values. Justify your answers. B, on what intervals, if any, is the graph of h concave up? Justify your answer. Part C, write an equation for the line tangent to the graph of h at x equals 4. That should be right in our wheelhouse. We've written only about 10 million equations of tangent lines since the start of the year. And then finally, part D, does the line tangent to the graph of h at x equals 4 lie above or below the graph of h for x greater than 4, and why? Okay, so go ahead and dive in. Let's um, so let's go ahead. I was going to say, you know, we don't necessarily have to like nail these in kind of linear order and like start with A and then on to B and C and D. And actually, I just worked these through with a couple of my other students, and they they kind of took a look at this, and I just said, well, you know, if you didn't have to go in order, which part might you start with? And they opted to start with part C. The only risk you run if you don't go A, B, then C, then D is that if you have, let's say, part C, and it depends on, you know, some work that you did in A or B, if you jump right to C, you might have to kind of backtrack and figure that out. So that, you know, could be one drawback and kind of jumping around a little bit. But if we look at C, I think we're going to have all the information we need just to dive right in and start with part C. So part C, again, asking us to write equation for a line tangent to the graph of h at x equals 4. So I hope whenever you see write an equation for a tangent line, you start out with point slope form of a linear equation. So that's kind of my starting point. Then I'm looking for my point of tangency, which is given as h at 4 equals -3. That's telling me that when x is 4, y is -3. And then my slope is going to be equivalent to h prime at the x coordinate that I'm interested in, which is going to be h prime at 4. So h prime at 4, I just kind of drop that in, I'm going to get, again, I'm looking at h prime of x, my equation for that. So h prime of 4 is going to be 4 squared minus 2 over 4. Okay, now I'm just going to take the information I have on the right, and I'm just going to drop it into my point slope form for my linear equation. So this is going to become y minus my y1 is -3 is equal to my slope m is right here. So I'm just going to write it like that. I'm not going to simplify anything because that just takes time. 4 squared minus 2 over 4 times x minus, and my x1 is going to be right there. Okay. And all they've asked me to do is just write the equation for the tangent line. They're not asking me now to like, okay, estimate a value for h at 4.1 or 3.8. They just want the equation for the tangent line, so I'm done. So I'm done with part C. Okay. Um, again, what I might do again, I don't need to be linear since we kind of got C out of the way. I'm going to go next to part B, and it asks on what intervals, if any, is the graph of h concave up, and then justify your answer. Okay. So part B. Well, I'm gonna. I always like to kind of sort of frame the answer to my question by kind of flipping the question back around. So I'm going to say H is concave up when H double prime, the second derivative, that's one thing I can look at, when the second derivative is what? When the second derivative is positive. Okay. So H is concave up when H double prime is positive. Um, this occurs, and then I'll drop in my answer. Okay. Well, what I need to do, since I'm looking to see an indication of where H is concave up by looking at the second derivative, I need to examine the second derivative and then look and see what interval or intervals, if any, um, the second derivative is positive. So I'm going to take the first derivative, which I'm given, and I'm going to take the derivative with respect to x of the first derivative. d dx, that. My left side is going to be h double prime of x is equal to, and on the right side, I'm going to need to use the quotient rule. So I'm going to bust out u's and v's. So I'm going to call my numerator u. I'll need to know what u prime is. Looks like that's going to be 2x. And then v prime is going to be 1. d dx of x is 1. Okay. And then the quotient rule, u prime v minus u v prime over v squared. And I'm going to kind of sandwich that right in between. So I want u prime, which is 2x, times v, which is x, minus u, which is a quantity x squared minus 2, times v prime, which is 1, all over v squared, which is going to be x squared. Okay. Now, I'm going to have to look at that, and I want to determine where h double prime of x is positive. So I do need to kind of clean this up a little bit. So if I simplify, I'm going to have 2x squared minus the quantity x squared minus 2 all over x squared, which I can kind of further simplify. If I distribute the negative, I'm going to have negative x squared plus 2. So I have 2x squared minus x squared plus 2. So when the dust settles, I'm going to have x squared plus 2 over x squared. So that is my second derivative. Okay. Now, I can save myself time. If I kind of look at my equation for the second derivative, because again, I'm looking for on what intervals, if any, is the graph of h concave up, and then justify your answer. I also want to kind of keep in mind that h, if I go back to the problem here, h is our function. It's defined for all x except x equal to 0. Okay, so x equal to 0 is not in the domain of my function h. Okay, so I'm only looking where h, as it's defined over its domain, um, is concave up. So I'm going to exclude. I'm not going to look at x equal to 0. So, but I'm looking at any other value for x besides 0. Well, if I look at that second derivative, think of it this way. Any number, again, the only thing excluded is 0, but any number that we plug in for x is going to give us, let's think about it. Let's just do one. If you go h double prime of 1, plug that in, we're going to get what? 1 squared plus 2 over 1 squared, which is going to yield 3, right? Which is obviously a positive number. Well, if we plug in -1, let's see what happens. So that would be -1 squared plus 2 over -1 squared, which is going to equal -1 squared is 1 plus 2 is 3 over -1 squared is 1. Again, we get 3, which is going to be, again, a positive number. So hopefully we can look at this and say, hey, gee, if we plug that in, any number, and then we square it, we're going to get a positive number in the numerator. Add 2 to that, still a positive number. And then in the denominator, same way. Whatever number it is, we're squaring it, we're going to get a positive result. So really, we're going to get h double prime at x is going to be, some positive value plus 2 still gives us a positive value over a positive value because we're squaring whatever our number is for x. So we get a positive over a positive, which is going to give us, so we're always going to have a positive value. So really what that tells us is what? Go back up here, we'll say that h is concave up when h double prime is positive, and this occurs really, we could write this a couple ways. We could write it negative infinity up to 0, not including 0, and then 0 to positive infinity. We could write it using interval notation like that. We could also say, or this occurs there, or when x does not equal 0. Okay? So really, we're basically saying that h is concave up everywhere it's defined. Okay. All right. So that it's not too bad. That's B. Now, if we jump down to part D, does the line tangent to the graph of h at x equals 4? That's actually, we came up with that equation in part C, right? The equation for the line tangent to the graph of h at x equals 4. So does that tangent line lie above or below the graph of h for x greater than 4, and then y? Okay, well, let's take a look at part D. Um, well, if we look at what we just found in part C, that h was concave up everywhere it was defined. So if I just sketch, doesn't matter whether I show it concave up increasing or concave up decreasing, it's not going to matter. I'm going to draw it concave up decreasing. I'm just going to say again, I have no idea what it looks like. I'm just saying this is h of x. The only thing I care about is that it is concave up everywhere it's defined according to the work that I did in part B. Now, what I'm doing is I'm going to add the tangent line. And so I am going to just say, hey, this point right here on my function is my point of tangency, which is 4, -3. Okay, that was my point of tangency. So I'm going to say that point is 4, -3. I'm just going to sketch my tangent line. Okay, pretend that's tangent. I can fix that by just making the point bigger. There we go. So that's the tangent line. Well, I'm looking at it, and it looks to me like my tangent line lies below the graph of h for x greater than 4. So I'm looking over, greater than 4, over in this area here, and it really wouldn't matter. As long as I'm somewhere on h and h is concave up everywhere, it doesn't matter that x is greater than 4 or x is less than 4. The tangent line is still below the graph of h. Now the y, well, again, what I would do is I'd kind of flip the question back as I'm writing my answer. And I would say the line tangent to the graph of h at x equals 4 lies below, okay, the graph of h. For x greater than 4. Okay, so I've kind of stated my answer. Now I have to answer kind of the y part. So I'm going to say because, okay, because why? Because really the second derivative, h double prime at x, I could just say h double prime, is positive for x not equal to 0. Therefore, h is concave up for all x that it is defined for. Okay. Okay. Um, nice. So part D, really not too bad. So what remains? Looks like part A. Find all values of x for which the graph of h has a horizontal tangent and determine whether h has a local max, a local min, or neither at each of these values. Justify your answers. Okay. Well, let's go ahead. Bring that down here. And I'm going to take this all with it in case we need to refer back to it. Okay, so I want to find, first off, all values of x for which the graph of h has a horizontal tangent, and then determine whether, so for each one of those, then I want to determine whether h has a local max or local min, or neither, at each one of those values. Then I want to justify that. Okay, well, kind of the key to this is what? H is going to have a horizontal tangent when? H has a horizontal tangent. H has a horizontal tangent when at f there, but there is no f in this problem, when h prime equals 0. Okay? So what I have to do now is look and see, okay, what x values, if any, cause h prime, the first derivative, to equal 0. Okay, so I'm going to take h prime of x is equal to x squared minus 2 over x. And again, I have the same restriction that I had for h, that x is not equal to 0. Okay? And we can see for h prime why we need that restriction, obviously, with the x in the denominator. Well, what I want to do is I want to set h prime equal to 0. And then, because really all I'm concerned with is the numerator. I can ignore the denominator for this. If that gives you a brain cramp, you could look at it like this. Say, okay, I'm going to set h prime of x equal to 0. I'm going to keep track of the whole thing. First thing you might do, multiply both sides by x. So I get x squared minus 2 is equal to 0. So I'm really kind of back to where I was, my starting point. Okay, now I want to add 2 to both sides. So 2 is equal to x squared. Then I want to take the square root both sides. Square root of x squared is absolute value of x is equal to square root of 2. And then to write it without the absolute value, I can write it as x is equal to plus minus root 2. Okay, so those are my two values of x that would cause my first derivative to equal 0, and therefore would lead to h having a horizontal tangent line. Okay. Now, what I want to do is I want to look and see so I'm going to kind of answer the first question. So I'm going to just say um, h has a horizontal tangent when h prime is equal to 0. Um, this down just a little bit. I'm going to say this occurs at x equal root 2 and negative root 2. Kind of just double checking that I don't have any kind of interval that I'm living in. Go back here. Nope. The only restriction on my domain is just that um, h is not defined for x equal to 0. So both of those values are kind of fair game. So at positive root 2 and at negative root 2, first derivative is equal to 0, and therefore h has a horizontal tangent. Um, now I want to look and see, are those going to be a local max, a local min, or neither at each of those values? Okay, well, what I can do, a couple ways I can do it. I have already come up with the second derivative. And I don't know if I would have gone in order. I calculated the second derivative here in part B because I was interested in the concavity. But since I've got the second derivative, I'm just going to use the second derivative to indicate, see if that's going to tell me if my critical numbers, because those are really critical numbers of h that I just found, root 2 and negative root 2, if those critical numbers lead to a local min or a local max. Okay, so I'm going to take um, this kind of simplified form of my my second derivative. So I've got h double prime of x is equal to x squared plus 2 over x squared. Okay. Well, and I guess I should already know the answer because we just said that, gosh, for all x not equal to 0, we said that the second derivative is positive, right? That was the work that we did with part B to talk about the interval where h is concave up. So that means if I'm plugging those into the second derivative and I see that h double prime at root 2 is positive, therefore, my conclusion is going to be what? Well, again, if this is concave up everywhere, then this value can only be a what? No, it's concave up. That can only be a local min at x equals root 2. It's a local min on h at x equals root 2. And then again, also because this is, doesn't matter if it's positive or negative. I'm sorry, it doesn't matter if the x is positive or negative. The second derivative is going to have a positive value. Therefore, I also have a local min on h at x negative root 2. Okay. All right. So that's kind of a little off the. I guess one other way I could kind of confirm that. Again, that might have been the quickest way to do it. But we could also look at the first derivative on either side of our critical numbers, our positive and our negative root 2. So if we look at that, let's think about that. We've got h prime at x is equal to x squared minus 2 over x. Okay. And I'm saying that my critical numbers for h are root 2, x equals negative root 2. Well, what I could kind of do maybe is look at this and maybe just have a number line where I'm going to just show my. Now again, I'm just not going to rely on my number line for my justification. But I'm just doing that just to kind of confirm what we've said here based on the second derivative. So I'm just looking at my number line, and then I'm just saying, okay, well, the h prime at x, the value, and that's this is my x, and so we just said that h prime at x is 0 when x is negative root 2 or positive root 2. Well, if I'm going to select, kind of just check, if I take 0 and I plug that into my first derivative, so h prime, you probably caught that before I did. Can't do it. Wouldn't be prudent because this is not defined for 0, so that's, can't check that value. But I can check any other value, and there's only an infinitude available, but that's the one I can check. I could put this 0, and that's going to be undefined for 0. But how about we check positive 1? Okay, positive 1 is in my interval between these two. So if I check 1 and I do h prime at 1, I'm going to get 1 squared minus 2 over 1, which is going to be a negative value. So that means my first derivative is negative on this interval. If I check, let's keep going this way. If I check 2, so if I do h prime at 2 is equal to 2 squared minus 2 over 2. I get 4 minus 2 is 2 over 2 is 1. So that's going to be positive. So I'm going to see on the other side of this 0, it changes and I get a positive value. Okay. Okay. And that would make sense that I'm going from a negative slope on h to 0, bottoms out, and then it becomes positive right here. So yep, that looks like a relative or a local min, just like I said. Now, again, just to kind of confirm that, uh, if I look over here, and if I know this is 0, now here's where I have to kind of be careful. If I check, I don't want to just necessarily assume that it's negative, the first derivative is negative from negative root 2 to root 2, positive root 2. So I'm going to pick a value at negative 1, and I'm going to see what my value of my derivative is. So h prime negative 1 is equal to negative 1 squared minus 2 over negative 1. So that's going to give me 1 minus 2, which is negative 1 over negative 1, which is 1, and that's a positive value. So really, that could have been kind of a little dicey. I could have maybe just made that incorrect assumption, but really in this interval here, from 0 to negative root 2, the value of my derivative is positive. Okay, it's kind of like what I saw over here. Now, if I go to the other side, and if I again use maybe negative 2, I plug that into my first derivative, h prime at negative 2 is equal to negative 2 squared minus 2 over negative 1. I'm going to get 4 minus 2 is 2 over negative 1, which is going to be negative 2. And so therefore negative. And so then on the other side of this, my derivative changes signs to negative. So I have the same thing that I had here, where my derivative went from negative to a positive. Same thing here, goes from negative to a positive. So again, we have a relative min also located at negative root 2. Okay. All right, guys. Hope that helps. That was from the 2001 exam, and that was question number 4. All right. Thanks, guys.